Hello everyone, my name is Ken in Madrid and today I'm going to present you one of the research projects we've been conducting at the Sustainable Ruminant Nutrition Lab in the Animal and Food Science Department at Texas Tech. The project is the effects of bismuth subsalicylate on ruminal fermentation of cattle consuming a feedlot diet. And the reason why we conducted this experiment is because some byproducts that are commonly used in the industry to feed cattle can contain elevated levels of sulfur, such as the case of distiller grains that are used from the ethanol industry. Research has documented that high levels of sulfur in the diet can lead to some metabolic disorders. These disorders go from poor performance to inadequate mineral absorption, and can even cause sulfur-induced polyencephalomalacia. Sulfur-induced polyencephalomalacia is thought to be caused by elevated concentration of hydrogen sulfate gas in the rumen, as it was presented in an article in 2012 by Drunowski titled Dietary Sulfur Concentration Affects Rumen Hydrogen Sulfide Concentration in Feedlot Steers During Transition and Finishing. However, an article published in 2020 by Henry et al. Titled The Effects of Bismuth Subsalicylate and Encapsulated Calcium Ammonium Nitrate on Ruminal Fermentation of Beef Cattle reported that bismuth subsalicylate, or BSS, binds to the sulfate in the rumen, decreasing its detrimental effects. To evaluate the effects of bismuth subsalicylate, or BSS, found in the literature, we perform a 3x3 Latin square experimental design where cattle were given 3 different diets. The first diet was a controlled diet with a sulfur content expressed in dry matter basis of 0.27%. The second diet was a high sulfur diet with a sulfur content of 0.38%, expressed in dry matter basis as well. And the last diet was the same high sulfur diet, but this time treated with bismuth subsalicylate, or BSS, at a concentration of 0.33%, again expressed in dry matter basis. Once the animals were assigned one of these 3 treatments, they were fed such diet for a 14-day adaptation period from day 0 to day 13. On day 14, ruminal cap gas samples were collected every 4 hours for 12 hours. And on day 15, ruminal fluid was collected and ruminal pH was measured every 3 hours for 24 hours. Those samples were later analyzed in the lab to determine hydrogen sulfide concentration, ammonia nitrogen concentration, and ruminal volatile fatty acid profile, or the VFA profile. And the results are shown in the graphs and in the table in this poster. So the first graph shows the effects of BSS on ruminal pH. And as observed in the p-values, a tendency of treatment effect was observed to affect the pH. Also, a time effect was also reported, but no treatment times time point interaction was seen. In a similar fashion, the effects of BSS on ammonium nitrogen was also evaluated. And treatments show a tendency to affect the concentration of ammonium nitrogen. We can see in this graph that both high sulfur and bismuth diets tended to have a concentration of ammonium nitrogen lesser than that one of the control diet. A time effect was also observed in the effect of BSS on ammonium nitrogen, but no treatment times time point interaction was seen here either. This is really important because this shows that sulfur or elevated amounts of sulfur in the diet do affect the fermentation profile of cattle. We can see here that both bismuth and high sulfur diets, which had elevated levels of sulfur, had a lower concentration of ammonia and nitrogen compared to the control, and this difference was seen statistically. The next graph shows the effects of BSS on hydrogen sulfide. And here we can see that treatment tended to affect the concentration of hydrogen sulfide. We saw that both bismuth diet and control diet had a concentration of hydrogen sulfide that was statistically lower, or show a tendency to be lower than the high sulfur diet. This is also important because it matches what it has been reported in the literature, that bismuth can bind to the sulfide to decrease the production of hydrogen sulfide, and therefore decreasing the chances of developing sulfur-induced polyencephalomalacia and other metabolic disorders associated with high levels of sulfur in the diet, such as inadequate mineral absorption and also poor performance. Finally, the table here presents the BFA profile obtained for each treatment. We can see that there was no treatment effect observed in total BFA production, nor in the concentration of propionate, butyrate, valerate, and caprioate, or in the molar proportions of the major BFAs. However, we did see a tendency of the treatments to affect the acetate concentration, and also a tendency to affect the brain chains fatty acids as well. In conclusion, it does seem that bismuth subsalicylate, or BSS, can decrease the formation of hydrogen sulfide production in the rumen without affecting in a negative way the fermentation profile. However, further research is needed in this area. And the reason why this is the case is because even though in this metabolism study, we determined that adding BSS to the diet does indeed lower the production of hydrogen sulfide, further research is needed to see how cattle perform when they are given a BSS additive to the diet. Furthermore, this shows a possible solution to treat diets that are high in sulfur, such as those where distillers grains are used as a primary component of the diet. If producers can use bismuth in such diets, they might lower the chances of having cattle with sulfur-induced polyencephalomalacia and overall having better performance of their cattle. Thank you.